Don't sit in the back. Asymptotes are horizontal, vertical, and or diagonal lines that represent values, specific values of x that affect the function. We first talked about the vertical asymptote. What does the vertical asymptote tell us?
What x values are out.
Lists any restrictions on the domain or the x values. Why? How does it do that? Because what is the vertical asymptote? How do you find it? How do you find the vertical asymptote? Nope. Nope. Because remember, the vertical asymptotes are any restrictions. Solutions are not restrictions. The solutions are the solutions, what you're looking for. So we can't use the restrictions. Can't use solutions in that one. How do you find the vertical asymptote? Very good. Very good. Excellent. It's found by setting the denominator equal to 0 and solving for x. So the vertical asymptote, any x that makes the denominator equal 0. This is how you should take everything we just talked about. This is what should be in your notes. When you take notes, don't just copy word for word for word. Take it and summarize it in your own words so you better understand it. If not during class, then do it immediately as soon as class is over. You should rewrite your notes. So the vertical asymptotes are any x values that make the bottom equal 0. Why is that a bad thing? Why can you not? Why is that possible? Anything divided by 0 is equal to infinity or undefined. How many times does 0 go into A or some number? Infinite. So that's why we say it's undefined, because infinity is not defined. Okay, so that's how you find the vertical asymptote. That's what we did last class. Now we're going to summarize the last two. We have the horizontal asymptotes. Can you have more than one vertical asymptote? Yes. Can you have more than one horizontal asymptote? Okay, well, then if you answered that, what exactly is a horizontal asymptote? How do you find it? The what? If you said it, okay, I'm glad you said that. If you set the numerator equals 0, what does that find for us? But think about it. We have the numerator over denominator. If we set it equal to 0, we found the solutions or the x-intercepts. So we find the x-intercepts by setting the top equal to 0. So no. No. We haven't talked about it yet, but no. Yes. So the bottom equals zero is a vertical asymptote, but the horizontal asymptotes has nothing to do with setting anything to zero. The horizontal asymptotes, first off, there's two important concepts. If I give you this function here, 1 over x, as x goes to infinity, 1 over x goes to what value? As x goes to infinity, what does 1 over x equal? Very good. You looked at the graph, didn't you, in your head? Perfect. Goes 0. Excellent. Why? What does the graph of 1 over x look like? Yeah, it's got a vertical asymptote because x cannot be 0. It's got a vertical asymptote at 0, and a horizontal 0 asymptote also at 0. But as x goes to infinity, what values on y is this graph approaching? It's getting lower and lower and lower. It's going to lower to what value? 0. Yeah, so whenever you have 1 over x, or anything, even if you had x to the 5th over x to the 7th, if you simplify this, what do you get? One over x squared. Because there are 5 x's on top, 7 on the bottom, we can subtract 5 x's on the bottom. So we're left with 1 over x squared. Now, as x goes to infinity, this value goes to what number? Think about it. 1 over x. 1 over 1 is 1. 1 over 10, 1 over 100, 1 over 1,000, 1 over 1,000,000. What's happening to the number? It's getting smaller. It's getting smaller and smaller and smaller and smaller, getting close to 0. Does it ever equal 0? No. But it approaches it. And so that's what we say. It just, instead of saying equals 0, it approaches 0, and that's our value. So whenever you have more x's on the bottom, it goes to 0. What about if we had x over 2 as x goes to infinity? This function goes to infinity. 1 over 2, 10 over 2, 100 over 2, 1,000 over 2. It still gets bigger, even though divided by 2. So it's going to infinity. So you see the difference between this one and this one? When the x's are more on the bottom, it goes to 0. If there's more of them on top, it goes to infinity. That's what the horizontal asymptote is defined by. The horizontal asymptote is determined by the leading terms of the top and bottom. So let me show you two separate polynomials. So that's P of x over Q of x. Remember, we always write the polynomials as that. when you look at a polynomial, what part of that polynomial tells you what the graph looks like about the function? The leading term. The leading terms are the most important because they have the highest power. That's where the degree comes from. So the rest of this stuff really is not that important. Well, because the majority of the function of the polynomial is dictated by the coefficient, the leading term, and degree and coefficient. The rest of those just simply add the curvature to it. That's another thing. But when it comes to horizontal asymptotes, it all depends on the leading terms. So what that gives us is this. We have ax to the n over bx to the, let's call it m, because they don't have to be the same. They could be the same, they could be different. The horizontal asymptote is determined by the degree of the polynomials. The degrees of the polynomials are m and n. Remember, the degrees are the exponents. If the degree of the numerator is bigger than the degree of the denominator, the horizontal asymptote is what? That's got to be either. Well, so here's an example. 2x to the 5th plus everything else divided by 3x to the 3rd and the rest of the equation. If the degree on the top is bigger than the degree of the bottom, remember, the n is on top, m is on the bottom. If you simplify this, what do you get? Right. Now, as x goes to infinity, what happens to this equation? It goes to infinity because the top number gets bigger, bigger, bigger. So if the degree of the top is bigger than the degree of the bottom, there is no horizontal asymptote because it goes on to infinity. You get it now? Once you understand the concept of the 1 over n over 1, you see where they go to. This is super easy. What if they're equal? Is what? Kind of. Yes. It's going to be the coefficients. It can't be 1 because it's not always going to be the coefficients. Because think of it, if we had 2x to the 5th over 3x to the 5th, the x to the 5ths cancel, we're left with 2 over 3. It's whatever the coefficients are. For right now, yes. We can, depending on what type of equations you have. We're just looking at simple polynomials here. We can have more complex ones, but in this course, yes, we're gonna say there's only one horizontal asymptote. What if the top is less than the bottom? Very good. Very good. Because if we had 2x to the third over 3x to the fifth, we can cancel 3 of those. Yeah, and as x goes to infinity, this one goes to 0. Let's see if the horizontal asymptote is 0, what does that mean in our graph? Does not touch the x-axis because the horizontal asymptote is the y equals 0 equation. Y equals a over b. It's this is the equation of the line of the horizontal asymptote. Because they remember in the first chapter when we talk about horizontal lines, it's y equals whatever it crosses. So those them. Let me look for some examples here. Example 4. Find the horizontal asymptote of this polynomial. Because the degrees are the same. That's how easy it is. Okay, let's show how this is true. Remember, even though the rest of this equation is not important, why is it not important? Let's look at this. Ever finished? We use the same example. What's really happening? Why? What's really happening is this. The equation 7x to the fourth minus 10x squared plus 1 over 11x to the fourth plus x minus 2. Given any polynomial, we have a lot of x's everywhere. So how do we get rid of the x's? Divide each term by the largest degreed x. So what's the largest degree? X to the fourth. What we're doing here is we're going to divide the entire equation x to the fourth, x to the fourth. So the top number, each of the top numbers is divided by x to the fourth. Each of the bottom numbers are divided by x to the fourth. Can I do that mathematically? Yeah. Whatever you do to one equation, you have to do to the other one. Since I'm dividing each of the numbers on top, I'm dividing the bottom ones, I'm changing the same thing. So I'm actually multiplying by 1. So simplify. In the first one, what happens there? They cancel out. In the next one, so it's x squared on the bottom because we cancel out 2 of them. And the last one is x to the fourth. On the bottom one, those cancel out. We lose one X. And then the last one's the same. I just took each one of those equations divided by x to the fourth. Now, as x goes to infinity, what happens? This one goes to 0. This one goes to 0. This one goes to 0. And that one goes to 0. So we're left with -7/11. That's what's happening mathematically. Any questions so far? So when you're asked to find a horizontal asymptote, this is what's happening, is you're taking the numerator and denominator and seeing how they're related to each other with respect to their leading terms. Example 5. F of x equals 2x plus 3, x cubed minus 2x squared plus 4. What's the horizontal asymptote? Because
Because.
the bottom is bigger than the top. And so there's more x's on the bottom, so the bottom gets bigger faster than the top. So yeah, so find the horizontal. What's the vertical asymptote in this one? We have to take the bottom, set it equal to 0, and solve. But that'll be a problem. We have to use what we did in the last section with chapter 4.5 is we have to use the rational zero theorem. Because we're supposed to have 3 solutions, and then we have to use long division, synthetic division to find which ones work. How many positive answers will we have on the bottom? How many positive solutions? Why 2? Sign changes. It's positive to negative. That's 1. Negative. So we have 2 or 0. Because remember, whenever you have something, why do we subtract by 2? Because if you have a conjugate, if you have imaginary or radical, you have to conjugate pairs. 2 pairs, that works good. How many negatives are we going to have? Only change the coefficient. The shortcut is only change the coefficient of the odd exponents. Because what you have to do is change all the x's to negative x. If it's even, right? So the evens cancel out the negative. So the only one that changes is the first one. So it's become negative. We have negative, negative. That's not. So only have 1.
So why don't we change the 4 again?
It doesn't have an x. Only change the coefficients of the odd exponents. So we only have 1 sign change. So we can have either 2 positives and 1 negative, or we can have no positives, 1 negative, and
not all zeros.
2 non-reals. Imaginaries are radicals, right? Remember we did that table? Positives, negatives, non-reals. But we don't have any zeros because that one doesn't have an x. But right, you would put that in there. So it's 1. That's the degree. So that tells us how many solutions we're supposed to have. So once we know we have the negative answer, we're left with 2 answers. We can use quadratic formula to figure out that. Very good, very good, very good. How about this next one? Example 7. Oh, let's do 6. Let's graph this one. Let's graph this one. G of x equals 2x squared plus 1 over x squared. Mhm. So there are actually 5 things we have to look for before we get started in graphing this. 1, x-intercepts. 2, y-intercept. 3, vertical asymptotes. 4, horizontal asymptotes. 5, oblique asymptotes. We haven't talked about this yet. That's next. So what is my x-intercept in this equation? How do you find those? How do you find the x-intercepts? Set y equal to 0. Solve for x. But since we have a rational expression, when we set y equal to 0, we simply set the numerator equal to 0 and solve for x. So we have 2x squared plus 1 equals 0. Move the 1 over, so we have 2x squared equals -1 divided by 2. So we have x squared equals -1/2. Square root both sides. So x is equal to plus or minus I square root of 1/2. So what does that tell us about our x-intercepts? We don't have any. That means our graph is going to be either above or below the x-axis. So there's no physical x-intercepts. What about the y-intercepts? How do we find those? Set x equals 0. Solve for y. So if we set x equals 0, what do we get? Undefined. So there are no y-intercepts. This will be answered in the next one. What's the vertical asymptote? How do you find the vertical asymptote? Set the denominator equals 0. So we have x squared equals 0. So x is equal to 0. What does that tell us? We cannot use 0. That's my vertical asymptote. How about the vertical asymptote, horizontal asymptote? Is y equals 2. Because the degrees are the same. Let's look what we put all together now. Our vertical asymptote, which we can't use, is the vertical x equals 0. That's our vertical asymptote. Horizontal asymptote is at 2. We have no x-intercepts and no y-intercepts. Yeah, so is the graph going to be down here or up here? It can't be on the bottom, because if it's on the bottom, it has to cross the x-axis, which it can't. So we know if you don't know it, plot some points. And the right-hand side is going to be like the Atari symbol. So what's that?
Because that's what it looks like. If we look back to our graph and. Look back down.
We had one similar to that. Yeah. Okay, example 7. Find all of the asymptotes. 2x² minus 3x minus 1, x minus 2. Vertical asymptote. Horizontal asymptote. And the one we're going to talk about because of this one. So what's the vertical asymptote? So it's the equation x equals 2. Why? Because we set the bottom equal to 0 and solve for it. What's the horizontal asymptote? Yeah, so it doesn't exist because the top is bigger than the bottom. Because you're right, it would go to infinity. Except there's always an exception to the rule. Remember, we had a x to the n over b x to the m. If n is equal to if the numerator degree is equal to the bottom degree plus 1, we have an oblique asymptote. Oblique means slant. That's the diagonal one, right? In other words, whenever the top degree is bigger than the bottom by 1, whenever it's bigger than the bottom by 1, we'll have an oblique asymptote. Why is that? Because because of this, it's a fraction, we can do long division. We can divide these two equations. If we do long division, what do we get? What times x gives me 2x²? 2x. So 2x times x is 2x². 2x times -2 is -4x. What do we do next? Change the signs and add. So those cancel. 4 minus 3 is 1. Minus 1. Can we keep on going? Yeah. What times x gives me x? What kind of one? Positive one. Because we have to know what sign to put there. 1 times x is x. 1 times -2 is -2. Change the signs. This is our remainder. Ignore that. This is our oblique asymptote. Because if the bottom is ever smaller than the top by 1, we're always going to end up with a linear equation. It's always going to happen. So what does this graph look like? What does 2x plus 1 look like? Remember, that's how we started off the semester. It's a linear equation. How do we graph linear equations? The y-intercept is 1, so put a 1, put a dot on 1. What's the slope? No. 2 over 1. So up 2 over 1. So there is the oblique asymptote. So the oblique asymptote is 2x plus 1. Do we have a vertical asymptote? At 2. So as we have a vertical line there. So our graph will either be here like this and here, or in these small little v's. How do we determine which one? What are our x-intercepts? Our x-intercepts are made up from 2x squared minus 3x minus 1, set it equal to 0. So since the leading coefficient is not 1, we put that into both of those. If it's factorable. Opposite signs. What times what is 1? When you subtract them, you get 3. Well, we can't do that. It's 2 times 1. What times what is 2? When you subtract them, you get 3. What times what? Because maybe take the first term, 2 times 1. That's 2. So what times what equals 2? When you subtract them, you get 3. Doesn't work. So we can't factor. We have to use what method? Since we can't factor it, we have to use the quadratic formula. What is b? So it's negative of a negative 3. Negative 3 squared. A is 2 and C is 1. Over 2 times 2. Let me put this on the next page. So we have 2x squared minus 3x. A equals 2, B equals negative 3, C equals negative 1. So we have negative of a negative 3 plus or minus negative 3 squared, 4 times A times C over 2A, which is 2 times 2. Negative, negative makes it a positive. Negative 3 squared is positive 9. Negative 4, negative 1 is a positive 4 times 2 is positive 8. Three plus or minus the square root of 17 over 4. That's why it wasn't factorable. Are these imaginary or do they really exist? Yeah. What is the square root of 17? Approximately. Square root of 17 is what? Yeah, let's say 4.1. Because square root of 16 is 4. Square root of 17 is a little bit bigger. So we have 3 plus 4.1 over 4. 3 minus 4.1 over 4. Negative 1.1 over 4. What is 7 over 4? It's less than 2. So let's say it's 1.8. And this one's going to be some fraction of it. So in our graph, we know we have a vertical asymptote at 2. Up 1 over 2, up 2 over 1. So our x-intercepts are here and here. So our graph will look something like this. They always have to be opposites of each other. Because we know it can't be here and here because there's no intercepts there. Okay. Let's do a couple more examples. Because the rest of this section is just dealing with examples. Example 8. graph this one as well. 2x plus 3, 3x squared plus 7x minus 6. Remember, we're interested in these points. You don't have what?
You don't have, an oblique.
Ah, I'm glad you said that. Can you ever have an oblique and a horizontal at the same time? Why not? Because the only way an oblique works is if what? Is if the numerator degree is bigger than the bottom by 1. So we have x squared over x.
Without asymptotic. And
Because the top is bigger than the bottom, and in other words, it goes to infinity, it doesn't exist. The oblique asymptote only exists when the top is bigger than the bottom, which means that there is no horizontal asymptote. And only if the top is bigger than the bottom by 1. So they cannot happen at the same time. You can only either have a horizontal or an oblique. So what's my x-intercept? Take the top, set it equal to 0. Negative 3 over 2, right? So for the x-intercept, set the top equal to 0. How do you find the y-intercept? Yeah, only look at the constants. So we have 3 over negative 6, which is negative 1/2. So we know y equals 1/2. We know we don't have a horizontal. Do we have a horizontal asymptote or? No, well, we do because the bottom is bigger than the top.
I see, no, it's because you did your exact line.
Yeah, I was using this example. I kept myself confused. So the horizontal asymptote, since the degree of the bottom is bigger than the top, it's the line y equals 0. That's the x-axis. And that means we don't have a vertical asymptote. What's the, a horizontal, oblique. What's the vertical asymptote? How do you find the vertical asymptote? Set the denominator equal to 0. Well, we could factor this. So since the leading term is not 1, we put it in the first terms, 3x and 3x.
Then different signs.
Different signs because the second sign's a minus, and the bigger number gets a plus. So now we take the first term, so 3 times 6. 3 times 6 is 18. What times what equals 18? When we subtract them, we get 7. Yeah. 9 times 2, 9 minus 2. Very good. Okay, so everybody good with that so far? Now, can we factor anything out of these?
Yeah,
3 other, so we can take out a 3 on the first one, give us x plus 3. 3x minus 2. Since we factor, we don't need that 3 right there. Erase that, delete it. So these are my factors of my denominator. So what are my vertical asymptotes? Set both of these equal to 0. and solve for x. So my vertical asymptotes are at x equals -3 and x equals 2/3. Everybody okay with that so far? I mean, you look at, now we're putting everything we've done since week 1 together. X-intercepts, Y-intercepts, all that sort of stuff. So let's look at the graph. My x-intercept is where? -3/2, which is -1 1/2. So it's over here. That's my x-intercept. My y-intercept is -1/2. So that's down here. My vertical asymptotes. So at -3, that's my vertical asymptote. And at 2/3. Horizontal asymptote. It's the x-axis. So that's my horizontal asymptote. So far, so good. Now, looking at this on the outer, remember we talked about the end behavior earlier? Same thing here. You notice in the outside domains, we have this domain here, we have this domain here, and we have this domain here. You notice in the outer ones, there are no x-intercepts. So that means the graph's either going to be above or below the x-axis, above or below the x-axis. How do we determine that? Pick a value. So if I pick 2 and I put it inside the equation, 2 times 2 plus 3, 3 times 2 squared plus 7 times 2 minus 6, and work it out. So we get 4 plus 3, 4 squared, 2 squared is 4, times 3 is 12, plus 14. That's 26, that's over 20. So it's positive. So that means this graph on this side is going to be up here. Same thing here. We have -1, 2, 3. So we pick -4. Plug it in the equation. 2 times -4 plus 3. 3 -4 squared. 7 times -4 minus 6. I'm just really interested, is it positive or negative? So 2 times -4 is -8 plus 3 is -5. -4 squared is 16. 16 times 3 is 48. Minus 7 times 4 is 28. Minus 6. So that's going to be 34. 48 is going to be positive. So it's going to be negative. So it's going to be down here. And it's always going to have that shape. What do you notice about vertical asymptotes, the graphs of near vertical asymptotes?
We'll have like a parallel in between.
No, just, what I'm looking at is, as we get closer to the vertical asymptotes, the graphs go to either positive infinity or negative infinity. The graphs, as they approach the vertical asymptotes, either go to positive or negative infinity. So that tells us, since we have 2 intercepts there, our graph here has to cross both of those. So that's our graph.
Wait, it's allowed to cross horizontal asymptote.
Yes. Because it's not a set rule. Horizontal asymptote is, does the value of the horizontal asymptote of the function exist at -3/2? Yes. It's just a guideline because they can cross. And usually if it crosses, what has to happen is if it crosses, it usually tapers off to that horizontal asymptote. But because of the rest of the function is more powerful, yeah. So it's
But it
it's
has two vertical asymptotes, it can't go back to the horizontal asymptote.
right,
Okay. That makes some sense.
and it's just the way the function is structured. Sometimes we may see equations, we have a vertical asymptote here and here, and we have these intercepts. We can have a parabola inside there, but it's all dictated by the functions themselves. But since we only have one x-intercept and one y-intercept, it's a decreasing function at that point. Let's see. Let's look. Okay, let's look at that example. Example 9. G of x. I'm sorry, did I go too fast? I'm gonna put that back up there. Everybody okay? Yep. And put back up there. X squared plus x squared minus 1, x squared plus x minus 6. Graph that. Let me see how many more do we have. Yeah, what we're looking for is x-intercepts, y-intercept, vertical asymptotes, horizontal asymptotes, oblique asymptotes. So we're gonna have an horizontal or a oblique asymptote,
Or-
and it's gonna be what? What? Because it's the same degrees, and they're both just so it's coefficients 1/1. What's my x-intercept? Plus or minus 1, because we take the top number, x squared minus 1, set it equal to 0. And when we square root it, we get x equals plus or minus square root of 1, which is plus or minus 1. So our x-intercepts are plus or minus 1. Vertical, y-intercept, 1/6. Because it's just a constants. -1 over -6 is 1/6. Vertical asymptote. Are you sure? If we factor this out, it's x, opposite signs. What times what is 6? When we subtract them, we get 1. And the bigger number is positive, so it's 3 and 2. So x equals -3 and +2. So it pretty much guides us to what we need to graph. So my x-intercepts were at 1 and -1. The y-intercept is at 1/6. Vertical asymptotes are at -3 and 2. That's my vertical asymptote. Vertical asymptote. Horizontal asymptote is at 1. So you notice here, so down here, we know that this is going to look like this. Because we have a y-intercept and 2 x-intercepts. How about the outer bounds? Is it gonna be above that horizontal asymptote or below the horizontal asymptote? No, it has to be above, because if it was below, then we have to have an x-intercept.
Right, right.
So we know because there's no x-intercept, it has to look like this. If you don't see it, plug in some points. And there's that graph. Who'd ever thought 11 weeks ago you'd be able to look at these and do this much? That is amazing. If even if you have just a little bit of idea of what's going on here, that is the learning process. And I'm proud of you. Okay, let's do one more, then we'll move on to the next topic. Example 11. Graph this one. F of x equals negative 2x squared minus x plus 15 x squared minus x minus 12. So let's look at the easy ones. Which one of these five are the easy ones? Just by looking at the equation. What's first? Can we find the x-intercept just by looking at it? No, we have to factor the top. Can we find the y-intercept? No, we just look at the constants. So it's negative 15 over 12. They both have a 3 in common, so it's negative 4 over 5 over 4. That's the y-intercept, which is negative 1 1/4. Vertical asymptote? No, because we have to look at the bottom and factor it. Yeah, but we have to do some math. Do we have a horizontal or an oblique? Yeah, since those are the same, it's the coefficients. It's negative 2, which means we don't have an oblique asymptote. So that's just by looking at it. We finished 60% of these three just by looking at it. Zero math. So let's look at the vertical asymptote. That's the next easy one. Take the bottom, set it equal to 0. And let's see if we can factor it. So the signs are going to be opposite or the same? And it's negative for the big one. So what times what is 12? When you subtract them, you get 1. 4 and 3. So 4 goes on the negative, 3 in positive. Which tells us my solutions are negative 3 and 4. Very good. What's that?
That's like, no,
You just change the signs.
you just, I put numbers.
It doesn't matter because it's called a commutative property of multiplication. A times B is something as B times A. And then the x-intercepts. We do that by setting the top equal to 0. Okay, what you got to do first is factor out the negative. So it's 2x squared plus x minus 15. We have 2x and 2x. Opposite signs. And the bigger one's positive. So far, so good? Since the leading term is not 1, take that times the last one, A times C. So 2 times 15 is 30. What times what is 30? When you subtract them, you get 1. Yeah, 6 times 5, 6 minus 5. And on the first one, we can factor out a 2. Get rid of that 2. So those are my factors. What are my x-intercepts? -3 and 5/2. It's whatever that is divided by the coefficient. Okay, let's look what we have here. Then we'll go a little bit deeper in there and look at those numbers. So my x-intercepts are at -3 and 5/2, which is 2.5. Between 2 and 3. The y-intercept is at -1 and 1/4. The vertical asymptotes are at 4. And we have a vertical asymptote, the same place we have x-intercept. We'll look at that in a second. And my horizontal asymptote is at -2. If we look at our function, after we factored it, we got -x plus 3, 2x minus 5 over x plus 3, x minus 4. Because these cancel, that's what we call a removable discontinuity. In other words, it's no longer a vertical asymptote, but it is now a hole. Whenever the intercept and the x-intercept and the vertical asymptote are the same thing, that means something cancels on top and bottom. So what we have to do now is we look at the graph of this function. In other words, this vertical asymptote is gone. What's happening here, since we have an x-intercept there, a y-intercept there, which means it crosses here, it's a hole, but then it tapers off again. In other words, it becomes a hole at that value. And yeah, the rest of it's what we got. And then where's the other half of the graph? It's going to be below there, yeah. Actually, let me see. Let's look at these values here. That's there. So it should be approaching the vertical asymptote, the horizontal asymptote, I mean. Yeah, so there's a hole there. I usually think that's the horizontal, but that's the horizontal asymptote. So it's approaching the horizontal asymptote, but in place of that -3 at that graph, it's a hole. You notice it's still just approaching the horizontal asymptote. It's never going to cross that one. So far, so good. All right. So that's it for that section.